Today, we will talk about the Inertial Reference System, which feeds some of the flight instruments in modern aircraft. And in addition to this, it also serves as a navigation system, known as inertial navigation. Inertial navigation is a self-contained navigation technique, which uses a computer in conjunction with onboard sensors to calculate and estimate the position, heading, and speed of the aircraft in real time. It is considered as a self-contained system because it does not require any information or signals from external systems to operate, since, as we already said, it only uses information from its own internal sensors. Now, these sensors normally consist of gyroscopes and accelerometers oriented in the three axes, which measure changes in speed, attitude, and heading. In this case, we can say that the motion sensors are the accelerometers, as they will measure the speed changes in each of the axes. On the other hand, the rotation sensors are the gyros, as they will measure the angular rate in each of the axes. In summary then, we can say that the system is able to calculate the movement and speed of the aircraft around its three axes. This implies that knowing the initial position, the new position of the aircraft can be constantly calculated. Let's look at an example of this. Let's suppose here we have an inertial unit, which has its own internal sensors and the processor. Now let's say that after turning the unit on, it moves to this new position in relation to the initial starting point. In this case, the inertial sensors measure the direction and speed of the movement. With this information, and based on the time it took for the unit to move to this new position, the processor can calculate the distance traveled. Now, since we know the heading and the distance traveled in relation to the initial position, the new estimated position of the aircraft can be determined. And basically, this is the way inertial navigation systems work. Let's see a more practical example of this. Let's say that our aircraft is at position A. And as we can see, the coordinates for this point are 4 degrees north and 75 degrees west. This point will then be the initial position that the system will use as reference. Let's now say that the aircraft takes off and flies in this direction. In this case, the parameters of time, distance, heading, and speed for this leg will be calculated by the inertial unit. Then let's say that at this point the aircraft changes its heading and flies now in this direction. In this case, the inertial unit will also measure the corresponding parameters for this other leg. Now finally, let's say that the aircraft changes its heading once again, and now flies in this direction, until reaching position B. Taking into account the initial position, and the parameters measured by the inertial unit, the system can calculate the new estimated position of the aircraft, which in this case would be 3 degrees north and 74 degrees west. In this order of ideas, we could say that inertial navigation is a kind of dead reckoning navigation that uses sensors and a processor to perform the calculations. Now, it is important to mention that the position calculation process is constantly performed in real time, which means that the flight crew can monitor the flight path at all times. However, as with all other dead reckoning navigation techniques, this inertial navigation is not perfect. It has certain errors that reduce the accuracy over time. This reduction in the accuracy of the system is known as drift, and it consists of measurement errors that accumulate over time, making position estimations less accurate. Let's see an example of this. Let's suppose that the inertial unit is turned on and aligned at point A. At this point, it is assumed that there is no drift. Now, let's say that the aircraft takes off and flies for 1 hour until reaching position B. During this time, the unit's sensors will have presented small cumulative measurement errors, which means that the estimated position calculated by the system will not be exactly that of point B, but it will be slightly off, as we can see here. Let's say, for example, that the difference between the estimated position and the actual position is 1 nautical mile. In this case then, we say that the drift is 1 mile. Now, let's say that the aircraft continues to fly for another hour, until it reaches point C. Now, taking into account that the estimated position at point B already had a certain drift, the drift at point C will be even higher, in this case, 2 nautical miles. As we can see, since the system errors are cumulative, the drift increases at a relatively constant rate over time, which is known as drift rate. In this particular example, the drift rate is 1 nautical mile per hour. However, it is important to clarify that each inertial system has its own drift rate, depending on the accuracy of its sensors. Now, as we could see, drift causes the accuracy of the estimated position to become less and less accurate with time, which means that the probable area where the aircraft is located increases continuously with time after the initial alignment of the system. For example, here at point A, where the system is turned on and aligned, there is no drift, since we know the exact position of the aircraft. Now, if the system has, for example, a drift rate of 1 mile per hour, this means that after 1 hour of flight, the estimated position calculated by the inertial system will be within 1 mile of the actual position of the aircraft. In the same way, if the aircraft continues to fly for another hour, the estimated position of the inertial system will be within 2 miles of the actual position of the aircraft. So with this, after a certain time, the accumulated errors are so large that the accuracy of the system is excessively low and can no longer be used for navigation. This means that the more time elapses after the initial alignment of the system, the lower the accuracy will be. Up to this point, we have focused on the navigation capabilities provided by the inertial system. However, since it measures the movement of the aircraft around its 3 axes, it can also be used as an attitude and heading reference for the flight instruments. Some of the instruments that can be fed by an inertial system are the attitude indicator, the heading indicator, and the turn coordinator. Now, although so far we have talked about the general characteristics and functionalities of an inertial system, we must say that there are different types of inertial systems. In aviation, for example, we have the Inertial Navigation System, abbreviated as INS, and the Inertial Reference System, abbreviated as IRS. In this video we are going to focus on the IRS, since it is the most used system in modern aircraft. However, first we must see some of the characteristics of the INS. The INS, or Inertial Navigation System, uses mechanical gyroscopes and accelerometers to detect changes in speed, attitude, and heading. Now, in order to function properly, these sensors are mounted on a platform leveled by torque motors, to keep them aligned in relation to the horizon and true north. This means that despite changes in attitude and heading during flight, the platform will remain aligned with the horizon and true north. Now, since this system employs mechanical gyroscopes and accelerometers, the unit must incorporate correction systems to compensate for the effects of real and apparent wander. In this video we will not talk about the correction systems used by the INS. However, we must say that this increases the complexity of the system and reduces the accuracy in general, which implies a higher drift rate. Taking all this into account, we can summarize the disadvantages of the INS. First of all, it has a heavy and complex design, since it uses mechanical sensors. There is lower precision in calculations and estimates. The drift rate is high. It has longer warm-up and alignment times, since the platform needs to be aligned with the horizon and true north. It requires a manual entry of the initial position for the alignment. And finally, it has a more complex control panel. Now, it may seem that the system has many disadvantages. However, by the time the INS was developed, it represented a major advance in navigation systems, especially for long-range flights. Having already seen the characteristics of this system used in older aircraft, let us now look at the IRS. The IRS, or Inertial Reference System, uses laser or fiber optic gyroscopes, instead of the conventional mechanical gyroscopes. One of the main characteristics of these sensors is that they do not require to be on a level platform, which allows for a more compact and simpler design. In this system, the most important component is the IRU, which is the Inertial Reference Unit, since it contains the different sensors and the processor. Now, in order to function correctly, the IRU requires certain data, such as the initial position, which can be inserted either manually by the crew or automatically by the aircraft's GNSS system. This initial position is quite important, since it is based on this position that the system will make the position estimations during the flight. Another important parameter is the barometric altitude, as this is used to compensate for the inertial altitude calculated by the system. This information is normally provided by the air data computer, which we have already discussed in previous videos. Finally, the IRU also requires true airspeed information from the air data computer in order to calculate wind direction and speed. Now, although the IRS is considered as a self-contained system, it can receive data from other units to increase accuracy and compensate for some measurement errors. Now, using the received information, in conjunction with the unit's inertial sensors, and the formulas stored in the memory, the IRU calculates parameters such as the ground speed, distance traveled, estimated position, wind direction and speed, pitch and bank attitude, true and magnetic heading, and the inertial altitude. All these resulting parameters are sent electronically to the flight instruments, as well as to the navigation systems and displays. However, depending on the design, the IRS may also send data to other systems, such as the autopilot and flight director, the yaw damper, the anti-skid and auto-brake system, the centralized warning system, the flight management system, the flight data recorder, and the weather radar. Now that we have seen a brief description of how the IRS works, let's take a closer look at its sensors, starting with the laser gyroscope. This sensor consists of a triangular unit that emits two laser beams in opposite directions, which reach a detector in one of the corners, as we can see in the image. This design allows to detect the rotation rate of the sensor, or in other words, it detects how fast is the sensor rotating around one of its axes. This means that in general terms, it provides the same information as a mechanical gyroscope, without the need for moving parts. Now, the principle used to determine the sensor rotation rate is known as the Sagnac effect. To understand what the Sagnac effect is, let's look at the following example. Here we have a ring with a laser source at the bottom, and a detector at the top. Here, the laser source emits two photons at the same time in opposite directions, so since they travel the same distance at the same speed, they will reach the detector at the same time. This will happen as long as the detector is still, or in other words, it is not rotating around its axis. This way, the laser beams will cancel each other out upon reaching the detector. Now, suppose we have exactly the same situation, but now the sensor is rotating. In this case, one of the photons will have to travel a shorter distance than the other, so it will reach the detector sooner. In this way, since the laser beams do not cancel each other out, an interference pattern is generated in the detector. Now, to be exact, the system does not detect the time difference between the arrival of one photon and the other, but instead, measures the frequency difference between the two laser beams, as this will be affected by the distance traveled. However, we will not go into detail on this. Now, since each laser gyroscope measures the rotation rate around a particular axis, the IRS incorporates 3 laser gyroscopes, one for each axis of the aircraft. In this image we can see the laser gyroscope that detects the movement of yaw. We can also see the one that detects the movement of pitch, and although it is not visible here, we also have the gyroscope that detects the movement of roll. Now, as with these laser gyroscopes, the IRS also has 3 accelerometers, each one aligned with an axis of the aircraft to measure speed changes. However, it is important to mention that the accelerometers do not measure speed directly, but they can measure the acceleration, which is a change in speed. This way, speed and distance values are obtained by means of integrators. So in this case, initially the accelerometers will only measure the acceleration experienced in a particular axis. This information is used by the integrator number 1, which relates it with time to obtain the speed. Then this information is used by the integrator number 2, which relates it once again with time to determine the distance traveled. This process occurs in each of the 3 accelerometers, which are aligned with different axes. This way, it is possible to determine the displacement or distance traveled in each of the axes. The combination of information from the accelerometers, makes it possible to determine how far the aircraft has moved to the east, west, north, or south in relation to the initial position, which is extremely useful for navigation. Now, although the IRS incorporates more modern and accurate sensors, they still have some limitations and measurement errors, usually related to minor defects in the mirrors of the laser gyroscopes. However, compared to the INS system, which uses mechanical gyroscopes, this system is much more accurate, with a drift rate of approximately 0.6 nautical miles per hour. Now, a characteristic of these inertial systems is that they require an initial alignment. Since, upon power-up, the unit must first align itself and determine the aircraft's position, attitude, and heading. During this alignment process, the system has to mathematically level the accelerometers with the horizon and determine the direction of true north. Let's see how the unit performs these processes in more detail. Let's start with the leveling of the accelerometers. In this case, as the aircraft is completely stationary during the alignment of the IRS, the only acceleration detected by the accelerometers will be that of the Earth's gravity. This way, the system can determine the direction of the gravity vector, and then align the system with the horizon. And as we can see in this example, even if the aircraft is tilted in relation to the horizon, detecting the direction of gravity can mathematically level the system with the true horizon. Now, the other process that takes place during IRS alignment is the determination of true north. As we know, the direction of true north will always be perpendicular to the Earth's rotation, as we can see in this example. But the question is, how can the inertial system detect the direction of true north? Well, although the Earth rotates relatively slowly, this motion is detected by the laser gyroscopes. So during the IRS alignment, since the aircraft is stationary, the only rotation detected by the gyroscopes will be the rotation of the Earth. This way, these sensors will detect the direction of rotation of the Earth, and based on that, they can determine the direction of true north. However, as we know, in aviation the heading is normally measured in relation to magnetic north, not true north. So in this case, the system incorporates a database of magnetic variation and global isogonic lines, with which the direction of magnetic north can be determined automatically in real time. This means that the IRS can determine both the true heading and the magnetic heading. Now, this alignment process takes some time, which depends mainly on the outside temperature and latitude. But let's see why. Let's start with temperature. The system components must reach their normal operating temperature before starting the alignment. Thus, the lower the outside temperature, the longer it takes for the system to warm up and start the alignment process. On the other hand, latitude also affects the alignment time, since the closer to the equator, the easier it is for the IRS to detect the rotation of the Earth and therefore determine the direction of true north. This implies that if the aircraft is too far north or too far south, the alignment time will be longer. In general terms, typical alignment times for modern IRS systems are between 5 and 18 minutes, depending on the conditions we have just seen. Now, talking about the system layout, on IRS-equipped aircraft, it is common to have up to 3 independent systems for increased reliability and accuracy. This way, since each system is totally autonomous and independent, each will have different drift rates, which implies that the estimated position calculated by each system will be slightly different with time. In this case, the estimated position of each system is compared and an average position is calculated, which is commonly known as mix IRS position. Now, as with other computers, it is common to integrate the IRS with other units to complement the information and calculate other useful parameters. For example, the IRS can be integrated with an air data computer to obtain the air data and inertial reference system, which is abbreviated as IRS. This allows to calculate parameters such as the wind direction and speed, the ground speed, and the wind correction angle. Now, as the IRS is also a navigation system, it is also integrated with the rest of the aircraft's RNAV or RNP sensors and systems. Finally, each aircraft has a panel through which the IRS system can be controlled. However, the layout and functions vary depending on the design and manufacturer. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.